Graphs of polar equations can be the most interesting and intricate graphs in all of mathematics. Consider this polar equation, r equals 5 cosine 3 theta. To construct its graph, we might sort of think in the sense of function here, that r is a function of theta. That is, we have r, one of our unknown quantities, and we have an expression involving our other unknown quantity over here. And we're really not talking about functions here. We're just talking about an equation. These graphs are going to fail the vertical line test rather miserably in a lot of cases. So let's not think about that, but only in the sense of developing a table of values. So we have an expression involving theta here, and it looks like a rather intricate kind of expression. So we might build on our table of values, and our table of values is just this polar coordinates. You see, it's a table involving polar coordinates. So it's an r and a theta combination for graphing purposes. Now, I've got a theta column right here, and I'm letting theta take on values 0 through 60 degrees in 10-degree increments, just for discussion purposes here. And then I'm kind of building, notice I'm building along the top here, theta, 3 theta, cosine 3 theta, and then 5 cosine 3 theta. It's kind of a nice way to go through and build our chart for graphing. And by the way, we're going to approach this idea of graphing both from a by hand type method using graphing paper, and also using the graphing calculator. So we're going to look at both here, but if we're doing it by hand, then we kind of need to make a chart sort of like this. I'm going to show you another chart in a minute that streamlines things a little bit, but we want to notice a pattern developing here. Okay, so it's the idea of just taking and building on this little expression. So it's theta, then 3 theta, then cosine 3 theta, 5 cosine 3 theta. And once we get to 5 cosine 3 theta, this is r. So now we have our ordered pair for graphing, you see, our angle and our distance. Okay, now notice what's happening, particularly in this column. We're taking the cosine of some angles, and the value is going from 1 to 0, and then 0 to negative 1. That's kind of a predictable kind of thing. After all, we know that the cosine curve goes from the top of the amplitude to 0, and then the bottom of the amplitude back to 0, top of the amplitude, and so on. So this is kind of a predictable situation, and we want to notice where that incremental change is occurring. It's occurring here from 1 to 0 at 0 degrees to 30 degrees, but really, gee, where is this happening when we examine the cosine curve to begin with? Well, let's see, it started at the top of the amplitude at 0, and then at pi over 2. At 90 degrees, it went back down, you see, to the intercept. So why is it happening that it's taking only 30 degrees for that to happen here? Well, we can consider that, we can understand that by thinking that, gee, let's look at what happens from 0 to 90 degrees. Our angle, you see, is 3 theta. So dividing in all parts by 3, that all of the activity that is happening in between 0 and 90 degrees, you see, is happening now for a theta in our problem of 0 to 30 degrees. So our increments of 30 degrees are going to have some interesting things happening in them. All right, now let's go through and plot a few points. I'm going to show you some strategy. I'm developing a strategy for constructing graphs here. If we are taking the approach of using this table of values, then here's what we'd have to do. We'd have to look at this combination of 0 degrees and 5 and come over here to a coordinate plane. Now notice how I've built this. Now, let's talk about the coordinate plane for a minute. I've built a polar coordinate plane out of a rectangular coordinate plane. Now I have polar coordinate paper that I could use, and I might show that on another problem. But I want to show you that you can build your own polar coordinate paper, you see, even if you only have rectangular paper. And all you do is at each increment here, I'm just drawing concentric circles, you see, that are just out from that center called the pole. And then I took a protractor and I measured 30 degrees and made a mark here, and 30 degrees and made a mark here. You see, and here, and here. So I have some marks for 30-degree increments for reference. All right, so this allows us then to make a pretty accurate sketch of the graph. All right, at 0 degrees, the distance r is 5. So at 0 degrees, the distance is 5. So we start here. Now, at 10 degrees, I'm looking back over here, the distance is 4.3. All right, let's see. 10 degrees, that'd be an angle about like this. So we have, let's see, 1, 2, 3, 4.3 and 10 degrees. So that might be something like this. And then at 20 degrees, I have 2.5. So 20 degrees, here I am up here. The distance is 1, 2.5. And then at 30 degrees, I'm at 0, right here. So in this little increment of 0 to 30 degrees, the graph is changing, the distance is changing like this. You see, from 5 to 0. Now, here you want to kind of get your head into the notion that this graph is well, all graphs are kind of a dynamically changing situation, but especially here in polar coordinates. As that angle is changing, the distance is just coming in. You see, it's coming in to the pole. And now let's see what happens as we go through the next 30-degree increment. Well, let's see. We would look back over here and we would see at 40 degrees, the distance is negative 2.5. So at 40 degrees, the distance is negative 2.5, so we're going back 1, 2.5. There must be a better way to look at this. And there certainly is. That we can look at the situation in 30-degree increments and actually make part of the graph within each of those increments. And therefore set up a table kind of like this. As theta changes from 0 to 30 degrees, 3 theta is changing from 0 to 90 degrees. Very important interval here in terms of the graph of the cosine curve. And the cosine then of that angle 3 theta is changing from 1 to 0. Very important points from our experience with the graph of the cosine curve. And 5 cosine 3 theta is changing from 5 to 0. All right, and in a similar way, just go through a number of 30-degree increments here, 30 to 60 degrees, 60 to 90, 90 to 120, and so on. You see, and then here 3 theta is 90 to 180, 180 to 270, 270 to 360, very important points on the cosine curve. 1 to 0, 0 to negative 1, negative 1 to 0, 0 to 1, just as we would expect with the normal cosine curve. And then 5 times those values. All right, now we have something we can get a grip on in terms of the graph. All right, now notice that 0 to 30 degrees, we're going from a distance of 5 to 0. We've already constructed that part of the graph. Now, 30 degrees to 60 degrees, we go a distance of 0 to negative 5. So here's what's happening. So 30 degrees to 60 degrees, the graph is going from 0 to negative 5. Negative 5 at that point, gee, that's back this way, right here. So that graph, as we go like this, that distance is going like this. You see? Like that. And then in the next increment, from 60 to 90, from 60 to 90, we're going, and I'm just reading over there, negative 5 to 0. So from this point, we go back to here. And then in the next increment, let's say that's 90 to 120. What's happening? 0 to 5. 0 to 5. Right? 0 right here at 90. And then by the time we get to 120, we're out here at 5. So I'm sort of connecting those, but in a fashion kind of like this. You see, and then in the next increment, let's see, that's 120 to 150, we go 5 back to 0. So it's like this. And then from 150 to 180, you see in this little increment, we're going from 0 to negative 5. So again, it's 0 to negative 5. By the time we get to 180, it's negative 5. Now we have to keep this positive and negativeness idea in good perspective here. We have to understand that even though we have angles up here, distances can be down here to give us a graph down below the y-axis. So all of that has to be kept in perspective. Now, also, the whole cycle of this graph is occurring in 0 to 180 degrees. Some graphs you have to go 0 to 2 pi or 0 to 360 degrees. But this one has its repetitive nature occurs in a cycle of pi or simply 180 degrees. You'll kind of know when it starts to repeat, when you get a point that's back onto itself. You see, when you get the first point on the graph coming back to that spot. You might try one more increment, you see, from over here to verify that situation. Okay. Now let's use the graphing calculator to have a look at the graph. Now some graphing calculators can graph polar equations directly. That is, there is a polar mode on the calculator and we can enter r equals and then some expression involving theta. Yeah, we can just enter like this, r equals, and then just enter exactly what we have here. Now the calculator that I have does have that capability, but some calculators don't. And those that don't, a lot of times they will have a parametric mode, and so you could enter this equation as a parametric equation. And really, I'd like to show both situations here. The parametric equations associated with this situation are these. X is 5 cosine 3t times cosine t, and y is 5 cosine 3t times sine t. And so let's go to the calculator now. Let's use the parametric equations first. I've already entered the equations and I have already made some window settings. You'll notice from the T max here, you can suspect that I'm in degree mode because this is 180 degrees. Normally now for these, remember it's usually the case that we would set this up as 360 degrees for one complete cycle, but for this particular problem 180 will do fine. I set the step as for 5 degrees at a time. Now the other settings were made in order to achieve a square perspective, and I calculated that against the y minimum and max. The y min -5, y max 5 gives a total vertical distance of 10. And you know that to calculate knowing vertical distance of 10, multiply times 1.5 to get horizontal distance. Well, 1.5 times 10 would be 15. And splitting 15, we get 7.5 on either side, and that's why the x min is -7.5 and the x max is 7.5. Well, here is our graph. And pressing trace and cursoring over to the right, we can see how our t value is changing. This is 10 degrees, 15 degrees, 20 degrees, and so on. And as I get down into this area, let's say t of 60 degrees, I have a position given by x and y. Well, you know, we have been talking about positions in terms of polar coordinates, so we could make that change here. We could change to polar coordinates like this. Now, on some calculators, this is found in the mode menu, and other calculators, we find it like this. Press. Now, it's right in here in the format, but I don't press format directly or press this zoom directly. I press second and then the zoom button for format, and up at the top I'll cursor to the right from rectangular to polar and press enter, and then go back to the graph, and then pressing trace, I notice that the position you see of that point is in terms of an r and a theta. Now let's go back to the beginning here, and I want to show you something about how the calculator is writing the information. Here the t is 0 and the theta is 0. Here t is 5 and theta is 5. No big deal. As I cursor over to the right, those two are corresponding, and the r value is the distance you see from the pole to that point. But as I get over in this area where I have a t of 45, notice that t is measuring the angle sort of positively like this, whereas the position angle is given as a negative angle because the calculator is causing the r value to always remain positive. And that's kind of an interesting nuance within the calculator. You see, this theta is being measured negatively in this fashion, and then the r value can be given as a positive number. So, you know, what we would have done a little while ago, we were alluding to the idea that we would have measured that angle as 45, and then we would have taken the r distance to be negative from the pole, you see, in this direction. So at any rate, we get to the same point. Let's change to the radian mode. Let's go to mode here and go down to radians and press enter at this point. And then we need to make some accommodations with our window settings. I'd like for the T max then in radians to be pi, and that's approximately 3.14. And then I'll set the T step to be 1/10. And now our graph. And on trace, we can see a similar thing happening that happened before, that the T and the theta are corresponding nicely in this area of our graph, but as we go over here into the third quadrant, we have T as a positive angle, and that positive angle is just generating the points that are being plotted on our graph according to these parametric equations. And the theta down here is a position idea, that the R and the theta is giving the position of the icon. So, and that theta is in terms of a negative measured angle in radians. So it's from here and measuring in this direction so that R can remain a positive value. Well, at any rate, you know, we mentioned that we can enter parametric equations to give rise to this graph that we looked at, this polar equation generated graph. But some calculators are able to enter polar equations or have polar equations directly, and this calculator is one of those. In mode, if I cursor down, and this is function, here's parametric, oh, here's polar. So if I press enter, you see, and then y equals, I can enter the polar equation that we talked about earlier. So it's 5 cosine 3 theta. And if we go to the graph, it looks like this. Oh my! Again, when the graphs kind of look like they have a life of their own here and something comes up that's unexpected, it's usually a missed correlation between radian mode and degree mode. So here we have, let's see, we're in radian mode here, but on our window settings we're setting up for degree mode, you see. So we have a bad correlation there. Let's go back to mode and reset to degrees. I'll press enter here, and in the window settings we see that we have 180 and our theta step is 10. I'd like to change that step to 5, I think, to have a little more accuracy. And the graph then has the appearance that we expected. And let's see, tracing, we have our distance and theta, you see, as we would expect. Now notice in this mode we're talking about the distances as being negative here and a theta as being positive. So it's just a little bit different than we found in the parametric mode just a little bit ago. And we could change back to radian measure and we would find the same kinds of things. We could trace along and get distances and angles in terms of radian measure if we so decide. Early in this textbook, when we first started studying the graphs of equations on a rectangular coordinate plane, we got some mileage out of identifying what kind of symmetry we had, x and y intercepts and such things as that. We can go through the same kind of analysis here with polar equations. Consider the idea of symmetry. Now, the graph that we saw just a few moments ago, this graph, was symmetric to the horizontal axis. This is called the polar axis. And to examine the idea of symmetry about that polar axis, we might use the same kind of approach that we did when we talked about symmetry with the x-axis on our rectangular plane. That is, we know that conceptually we have symmetry about that horizontal axis if we can fold the graph onto itself. And that folding onto itself leads us to the idea that a point in this position will fold onto a point in this position, and that points on a graph correspond with truth in the equation. So as long as, now let me use the xy plane for a second here. If xy is on the graph, then x negative y is on the graph. And we said to test for this kind of symmetry, what we can do is plug this x negative y into our equation, and if the original equation is equivalent, then we have symmetry about the x-axis. You see, so that's the idea. If we have an equivalent or the same equation evolves, then we have that kind of symmetry. Okay, now we're dealing with a different kind of situation, though. We're dealing with an r and a theta. But the notion is exactly the same. That is that this is some r theta. Now, what's this in terms of r and a theta? Well, let's see, it's a distance here, but the angle is just a little different. Gee, it could be an r, oh, it could be a negative theta, you see, because here's our angle. Let's look at it over here. Here's the r theta. So here is our angle theta. And that's our distance r. Well, down here, if we're thinking about a point that reflects in this polar axis, you see, then our angle is negative theta, and our distance is still r. So it's the notion that if r theta is on the graph, then r negative theta is on the graph, and so we can test for this by putting r negative theta into the equation to verify that it's the same equation that we got before. You see, that it's equivalent to the original equation. All right, so that turns out to be the test. Now the trick here, the little nuance involved in polar equations is this, that there are a lot of ways of describing that same point. You see, because we have negative distances, and we have negative angles, we have negative distances, we have 180 degrees out on our angle. So really, an angle like this, you see, we could be thinking about an angle like this of theta and a negative r. You see, so that's another way to think about that. Now, what about this angle of theta? How do we generate that? How big is that? Well, we take it like this, that this angle, this reference angle, is the same as that theta over there. You see, and you get to this point by taking this 180 degrees and subtracting theta, you see, to get to that. And or it's pi. You see, it's an angle of pi minus theta, and then it's the negative r. So it's negative r is associated with a pi minus theta. You see, and so we could make the replacement like this into our polar equation to verify that we have the same as the original equation. All right, the replacement on our problem would go like this. We start out with our equation. Now, we're replacing r theta with r negative theta. So r theta is replaced with negative theta. So this becomes negative 3 theta. But we know that the cosine of the negative of an angle is the same as the cosine of the angle itself. And therefore, this is indeed the same as 5 cosine 3 theta. This is a relatively easy analysis. They get a little more difficult than this. Anyway, that's the test for symmetry about the polar axis. Now, what about symmetry about the line theta equals pi over 2? You see, we would have symmetry kind of like this. Now, let's look at that situation. You see, if it's the idea that if r theta is on the graph, then boom, we fold over this way, then that point needs to be on the graph. Well, let's see, how do we generate that point? Well, that's that idea of this, let's see, if we're using the same r, then that rascal right there is pi minus theta. So this is pi minus theta is on the graph. And there's another way to do it, though. There's another way to find this point. We could generate the angle down this way, you see, and have a negative r. So this could be negative r, negative theta. All right. Now, it's getting, I know that it's probably getting rather confusing right here. And you might be thinking, well, gee, if we go to all of this trouble to discover symmetry, why don't we just graph the thing and we can see by observation whether or not we have symmetry. But sometimes we do want to do this algebraically. Now, there's a third kind of symmetry. Now, the third kind of symmetry, and I'm a little bit thick with stuff up here, so let me take some things off. The third kind of symmetry corresponds with our past experience of symmetry about the origin. Now remember that kind of symmetry was kind of like this. A graph that looks something like this would have symmetry about the origin. And it's a double fold idea. If we're thinking about folding and symmetry associated with folding, if we fold the graph down this way, then it would look like this. And then if we folded this over here, it would fold onto itself. So it's the notion that a point xy is on the graph tells us that a point negative y, negative x, see this is the point then negative x, negative y is on the graph. And to test for this kind of symmetry in our past experience, we replaced x with negative x and y with negative y, and we verified that the original equation was equivalent to that. Okay, so it's a similar idea here. If we want to test for symmetry about the pole, then we consider that, let's see, a point, all I need really is the third quadrant here, but this can look confusing. Okay, if a point in the first quadrant like this r theta is on the graph, then fold, you see that point would be about right here. You see, so this guy is on the graph. Now how do we describe that that spot with a theta and an r? Well, there are probably going to be two ways to do that from our past experience, and certainly there are. But let's see how that would happen. Now this r is the same as that r, but what about that angle theta? Let's see, we have a theta here. It looks to me like, let's see, we have there's the theta, and here's the theta right in here as a reference, and oh, it's pi plus theta. So it would be pi plus theta r is one way to do it. Now let's see, there's another way to do it using a negative r value. Oh, it's just take the theta and negative r. So we could describe this point as a theta. Oops, I'm juxtaposing these, and I'm also full of my conversation here that I forgot about that. I should be writing the r value first. Let me go back, let me backtrack. It's the notion of r then, and let's see, that it was pi plus theta. There we go. And then with that negative r notion, it's theta with a negative r. So it's negative r with the original theta. So okay, we plug either of these into the equation and verify that we have an equivalent equation to the original. Now, to sum up, here's the idea. To test for symmetry with respect to the polar axis, that's the first one we did, we replace r and theta with r negative theta or this other replacement that we talked about. Now, I don't suppose that you're going to go through and memorize these replacements, but I really would encourage you to think through that process of thinking, okay, if we have symmetry about the, let's say the vertical axis, the theta equals pi over 2 line, then what happens in terms of the theta and the r? How can we describe a point that reflects over to the other side like that? And use what you figure out as the replacement rather than memorizing this. You ought to understand it conceptually rather than from memorization. All right, but at any rate, these are the various replacements for the different kinds of symmetry that we can have. Now, we do get some mileage out of some situations, situations involving cosine, for example, because the cosine of an angle is equal to the cosine of its negative counterpart. Generally speaking, if our polar equation has only cosine of angles involved in it, then we're going to have symmetry about the polar axis. And in a similar way, for those that involve only sine, we're going to have symmetry about the vertical axis, the line theta equals pi over 2. All right. Another aspect that can be evaluated before graphing, and sometimes this is helpful, if for no other reason than to set up your graph paper, is to figure out the maximum r values. Now, to figure maximum r values, all you do is go through and analyze the greatest and least value that the trig function can take on. Now, cosine theta can take on values. You see, for different angles, what values do we get for the cosine of theta? Well, it varies between -1 and 1. So let's take the extremes. If cosine of theta is -1, you see -1 times -2, that would be 2. 1 plus 2, that's 3. Okay, now what about the other extreme? For the cosine of theta could be 1. If it's 1, we have -2 times 1, that's -2. 1 minus 2, that's -1. What's the largest value? You see, now in terms of distance, by the way, that -1 that I found is still a distance of 1 from the pole, isn't it? Now it's just taken in a negative direction, you see, from some angle, but distance from the pole, it's kind of like an absolute value. You see, you think of it as 1. So the maximum value, though, is found when cosine theta takes on the value -1, in which case we have an r value of 3. So the maximum r then would be a distance of 3 from the pole. For 5 cosine 4 pi, well, let's see. Now don't let the 4 pi idea scare you. It's just 4 times some angle. It's just a bunch of angles that we have over here that we're taking the cosine of. But the cosine of angles, no matter how we describe them, change from -1 to 1. You see, and so let's see, if this value turns out to be -1, 5 times -1, -5. Distance from the pole, 5. If this angle, see, that for its maximum value, or the greatest value that this could take on would be 1. 1 times 5, distance of 5. So the maximum r that this can take on would be 5. Okay, let's consider a problem. Let's go back to the graphing calculator now, but before we do, let's analyze a couple of things. We have r equals 2 plus 4 sine theta. Now, because our expression here contains only sine, the sine, you can look at the SIGN pattern for the sine curve, or in what quadrants is the sign positive and negative, to discover aspects of this symmetry idea. But it's the notion that when sine is involved, SIN, sine is involved, the sine function is involved, that we have symmetry about the theta equals pi over 2 line. So here we're going to have, this is symmetric to the pi over 2 line, the maximum r value. Well, let's have a look. Sine theta can take on values from -1 to 1. If the value is -1, -1 times 4 is -4, 2 with -4 is -2. So the distance there is 2. Let's keep that in mind. All right, now sine can take on the value 1. 4 times 1, 4. 4 plus 2 is 6. Okay, 6 or 2, oh, it's going to be 6. So the maximum r is 6. Now, when does that occur? Well, we can tell when that occurs. Now, sine is, let's see, that 1, sine of the angle, occurs when the angle is how big? Well, let's think about the sine curve. It starts out at the intercept and it goes to the top of the amplitude. That's where it's 1. Okay, top of the amplitude occurs at pi over 2. So at pi over 2, that's going to occur. Okay, so we get this max when theta is pi over 2. Well, once again, we can enter the equation like this, or we can enter in the parametric mode our 2 parametric equations, and they are equivalent to one another. Let's go through and let's jump on the parametric equations first and have a look at the situation on the calculator. The calculator is set on parametric mode, and I have entered the equations. I'd like you to notice that I have contained this binomial 2 plus 4 sine t within a parenthesis in order to maintain the integrity of the equation. And I've done the same thing on the y equation. And for the window settings, now I'm taking a chance with this graph, and I'm thinking, well, maybe this graph completes one complete cycle in 180 degrees. And this is I'm thinking degrees here because I certainly would not set up 180 radians, so I'm thinking in terms of degrees, and my step is 5 degrees at a time. I set up x minimums and maximums and so forth according to a square perspective. You can have a look at them here if you're, just in case you're setting up your calculator the same way. X minimum -6, x max 6, y minimum -1, y max 7, and the graph has this appearance. Now, to check out whether or not the 180 degrees is enough, I'm looking to see whether the graph sort of completes itself and goes back into this point, goes back to this very point for one complete cycle. And no, it kind of starts here and ends there, and therefore I don't have a complete cycle. So I'll go back to the window menu and set this up as 360 degrees. A little bit of experimenting here will serve a good purpose in being able to tell whether or not we have a complete cycle. Oh, the graph kind of loops within itself here, and now it goes back to its beginning, and yes, we do indeed have one complete cycle. I'd like you to notice that we have a vertical line of symmetry here. We have that line of symmetry at theta equals pi over 2 as we expected, because our original polar equation was a function in terms of sine. But now we set up parametric equations here because some calculators are unable to write polar equations. Well, our calculator is able to write polar equations, so we'll go to that mode and we'll look at a polar equation, and then we would set it up like this. Now notice that the theta is in here as we would expect it to look. It looks like a theta, and this is what comes up when we're entering a polar equation and we press the variable key instead of an x or a t. Now it's a theta, you see, and so the graph then has the appearance that we would expect it to have. And we could go to the trace business, and we would get values or positions in terms of an r and a theta as we would expect to.